Okay, in this section, we're going to talk about Stokes' theorem, which is one of the major results of this course. So let's go ahead and jump in and motivate this a little bit with results we already know. So let's recall the fundamental theorem of calculus from Calculus 1. So this said that if I take a function capital F and look at its derivative, and then I integrate that derivative from a to b, the value of that integral is just f of b minus f of a. So the way we want to view this is that if I integrate the derivative of a function over the interval, it's completely determined by the values of the function at the edges of the interval, or at the boundary of the interval. So we want to think of x equals a and x equals b is the boundary of that interval. That's what's going to generalize here. So again, the integral of the derivative only depends upon the values of the function at the boundary of the interval. So another similar result we had to this was the fundamental theorem for line integrals. So in this case, we are integrating the gradient of some function, so we can view that as a derivative, over some curve given by a parameterization r of t for t between a and b. Then if I integrated that gradient, then all that came out of it was the difference of the function at the one endpoint minus the function evaluated at the other endpoint. So again, we can view the gradient of f as a type of derivative of f. It actually is legitimately a derivative of f if we view this stuff in terms of differentials, which we won't do in this course, but I do have some videos online explaining how that works. So if we view it that way, and we view this as a type of derivative of f, then once again we're saying if I integrate a derivative, all that matters is what happens on the boundary of the curve. So the values of f at the boundaries of that curve, the beginning point and the end point. So just to put this in the same framework now, we can view the interval a to b as a curve. We just say r of t is equal to ti, and let t go between a and b, and that curve there gives the interval a to b. So both of these examples, the fundamental theorem of calculus from Calculus 1, and then the fundamental theorem of calculus of line integrals, both of those just are saying if I integrate over a curve and I integrate the gradient of a function, then I get the difference of the function on the endpoints of the interval. So what we want to do is we want to expand this to move from one dimensions to higher dimensions. So now we want to integrate a derivative. We'll see what that derivative is. Derivatives in quotes here, so we haven't introduced it yet. And what I want to work with instead of a curve is I want a bounded oriented surface S. And I want to say, well, since this is a bounded oriented surface, it's going to have an edge. And I'm going to say I want to integrate a derivative in quotes over the surface, and I want to relate that somehow to what's happening to the function on the boundary of the curve, or on the boundary curve of the surface. So that's what we're going to do with Stokes' theorem. So first, let's go ahead and work with some bounded surfaces and orientations here to refresh our memory. So here's a bounded surface, S. The surface here is in green. And then notice, since it's a bounded surface, it has a curve C as its boundary. So the curve C here is given in red. So that's what we mean by a bounded surface with a curve as its boundary. So let's talk about orientation a bit now, because this is going to be important for us. So remember, we said that a surface was oriented if we could choose normal vectors all along the surface that were compatible. So basically, if I had a normal vector and I move just a little bit, the normal vector at the spot that I moved to is going to point in roughly the same direction. It's not going to all of a sudden flip and point in the opposite direction. So that's what we meant by an orientation. So the normal vectors vary continuously. And now if I have a surface with a boundary curve, if I have an orientation of that surface, that will also give me an orientation of the curve. And similarly, if we orient the boundary curve first, that boundary curve will give us an orientation of the surface. And so the way that we relate these two orientations is, as usual, we're going to use the right-hand rule. So we need to explain, what does the right-hand rule mean in this context? So here is our surface S and our curve C again. Now the two ways to do this are, first, if we have an orientation already on the surface, so we have this normal vector n pointing up, take your right hand and point your thumb in the direction of that vector n. Now curl your fingers, your right hand fingers, and the direction that those fingers are curling in is the orientation we're going to give C. So if my right thumb is pointing up here and I curl my right hand fingers, it's going to go in this direction, kind of going around the curve. And so that means along the curve, I'd want to go in this direction to have the matching orientation. And similarly, if I didn't have this n already and I had this orientation on my curve, if I take my fingers of my right hand and kind of curl them in the direction of the way we're traveling on C, then my right thumb will point up in this direction, and that will tell me the orientation on S. So we're going to want our surface orientations and our curve orientations to match, and that's what they mean. Just the right-hand rule here, again, to match these orientations up. So that tells us what we mean by orientation of the surface and orientation of the boundary curve. The next thing we need to do is talk about, well, what do we mean by this derivative that we had in quotes before? So this is what's called the curl of a vector field, and this is our derivative for this particular case. So let's take a vector field here, F, with P, Q, and R as my component functions. Then the curl is defined as follows. So we take the gradient here and treat it like a vector, and we take the cross product with F. So the cross product, we put the I, J, and K like normal, and then we put the components of the gradient here. So the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, and then we put the components of f down here. And now we treat this just like a cross product, except for instead of multiplying the components here, so if I covered I, for instance, this column in this row, then it would be the normal cross product would be this times this minus this times this, and then I. But these aren't things to multiply. These are operators. So what we say is instead of this times this, it's this applied to this. So the partial derivative of r with respect to y, and the partial minus the partial derivative of q with respect to z. And that's what we get here. And similarly for the other terms. So you calculate it just like you calculated a cross product before. The difference is we're applying the operators rather than multiplying here. But if you know how to do the cross product, it's easy to remember how to do this as well. And so the curl of a vector field essentially measures the rotation of the vector field. Again, we're not going to spend we're just going to take that for granted in this class. We're going to calculate a couple examples showing that it works out in the examples we calculate. But again, there's a video online that I made that makes this more rigorous of how it actually is calculating the rotation of the vector field. So now let's look at a couple of examples to see that it does work out that way, though. So we saw this vector field before. It's just xi plus yj plus zk. And this is the vector field where everything is just expanding away from the origin. So it's spreading out everywhere. And if you look at this vector field, there's really no rotation going on. Everything's just expanding out, but nothing's rotating around. So if there's no rotation, we would expect that the curl should be 0. And do remember, be careful here, the curl is a cross product, so it is a vector. So it should be the vector 0. And that's what we would expect for this since there's no rotation of this vector field. So let's go ahead and calculate that and see if it actually works. So first thing we have is, remember, this is our definition here, and I filled in the x, y, and z here for the components of my vector field f. And now this was our formula. So remember, cover up the first column and the first row, and then it's delta partial derivative with respect to y of z minus partial derivative of y with respect to z, I, and then so on. And we can see each of these x, y, and z are all independent variables. So z doesn't change if just changing y doesn't change z, and changing z doesn't change y. So both of these are 0. And similarly for the rest of these. So the entire thing we get out of this is just the 0 vector, which is exactly what we expected it to be because there was no rotation. Now let's go ahead and look at one where there is some rotation. So here's the vector field minus yi plus xj plus zk. So this one, recall, is rotating around, because if I got rid of the z component here, this would just be the vector field that rotates around the origin. But I've added the z component, so it's rotating around the origin, but it's kind of spreading out up in this direction, so kind of spiraling up. And if you're negative z, it's spiraling down. But it is rotating around the origin, so there is some rotation here. So we would expect the curl to be non-zero in this case. And just like before, let's go ahead and calculate the curl and see if it is non-zero. So again, we just put down the definition here where we fill in the components for f. And here's the definition working out with the cross product there, working out that determinant. And then we notice for the first two components, this is going to be 0, this will be 0, 0, 0. But this is going to be 1, and this is minus minus 1. So when we work all of that out, we get 2k. So the curl is actually non-zero in this case, just like we expected it. And one thing you can notice here is that if you were to take your right hand and curl it in the direction of the rotation, your thumb would point in the direction of k. So let's go back and look at that vector field again. Notice the vector field is going around in this direction. So if you curled your fingers in that direction, your thumb would point in the direction k. And so that matches up with what the curl is. So you can kind of see the curl is not only telling you whether there is or is not rotation, it's kind of telling you the direction the rotation is as well. So we're now ready. We can state what Stokes theorem is. We know what we mean by the surfaces and the orientation and the curves in the orientation, and we know what our derivative is going to be in this case. So let's go ahead and state Stokes theorem. So we're going to start out with a bounded surface S with a boundary curve C, and we're going to assume these two orientations agree, just like we talked about before with the right-hand rule. We're going to take a vector field F, and we're going to assume these functions P, Q, and R, those are going to have continuous partial derivatives in a region containing S. So just think of taking a little region around S, so making S kind of fat surface, so it has some volume around it. We want our component functions to have continuous partial derivatives in that region. So this is going to be the case in most situations, but we do want to be careful to check that just to make sure Stokes' theorem actually applies. In that case, what we have is if I take, so I wrote this in kind of the opposite direction of how we wrote the ones before, but if I integrate, so remember we're thinking of this here as a derivative, if I integrate the derivative over the entire surface, all that matters is what is the function doing on the boundary. So we don't, since we have a surface here, we don't just have 2 points for the boundary, we have an entire curve. So we can't just look at, the function at 2 points. We have to look at the function over the entire curve. But once again, we get only what happens, the only thing that matters is what happens with the function on the boundary here, the vector field function, of course. But so you can also kind of think of this as we have a two-dimensional object here. If we integrate the derivative over a two-dimensional object, it goes down to one lower dimension. So a one-dimensional object with the values of the function over that one-dimensional object. Our line integral ones, we had a one-dimensional object, the curve, and it went down to a zero-dimensional object, just the points on the boundary. And one thing to note here is, remember, we use this notation for the integral when we want to emphasize that it's a closed curve. So we do have to have a closed curve. The surface has to have a closed curve as a boundary here. So that's what Stokes' theorem says. Obviously, we're going to do a lot of examples of this in the regular lecture, but let's look at a special case of Stokes' theorem. This is called Green's theorem. And what this is rather than having a surface in 3 space, we're going to just take the surface to be in the xy plane. So that means it's just going to be a region R in the xy plane. And so in this case, we specialize this a bit. So we have a region R in the xy plane bounded by a curve, and we're going to take counterclockwise orientation for this. So if you use the right-hand rule, that means our normal vector is going to be k. We're going to take our vector field to be, it only has 2 variables because we're in the xy plane, so pxyi plus qxyj. And again, continuous partial derivatives in a region containing R. Then if we Stokes' theorem here, what this would say is the integral of f around the boundary curve here is the region over the surface, which is r, and then we have our derivative, and then we dot this with a normal vector here. In this case, our normal vector is just k. This is going to be equal to, and then we can go ahead in this case and calculate this out because it's not so hard since there's only x and y variables. And if we do that, the curl here is just qx minus py k, and then we dot that with k to get rid of that, and then we just have dA left over. So this is Green's theorem here. It simplifies significantly what Stokes' theorem says because we remove one variable. And as I said, notice the unit normal here is k hat. It doesn't vary with x and y because we're just in the xy plane. Let's go ahead and work one example of this. So let's take this vector field here. So we're going to take 3yi minus 3xj. And the curve here is just going to be this curve C, and we're oriented counterclockwise. So we're going around it in this direction, like this. So the region R is this region in here inside the curve. So we can just go ahead and do our calculations. We have qx minus py is equal to minus 6. So that's not hard to calculate based on formula for f. So then this is just our formula for Stokes' theorem in this case. And of course, we saw that this reduces to qx minus py. Qx minus py is just minus 6. So we're just integrating minus 6 over the region R. I can pull that minus 6 out front. So I'm just integrating the dA over R. And we remember that's just the area of R. So this just gives me minus 12 pi. And just recall that here, as I said, the integral of R of dA is just the area of R. And we saw R is a half a circle with a radius 2. So the area of that region is going to be 2 pi. So I just have minus 6 times 2 pi. So I get the minus 12 pi. Okay, so that's an easy version of Stokes' theorem using Green's theorem. We'll see how to do examples of Stokes' theorem in class. They're more complicated than Green's theorem, but we'll work through several examples.